to say that FEA is not really like, you take 3 credit classes and you're done with the FEA. Just like even for mechanical engineering students, I think the first year they take physics first, and then the second year they take the statics. Basically, it's like the force equilibrium and everything. And third years, they take the mechanics materials. So it's basically calculating stress, failure theory, and everything. And then the last year, before they graduate, they take the FEA. So it's, and also in our department, mechanical aerospace engineering, like in aerospace engineering, that program, FEA is not really required. So it's only required for mechanical engineers. So it's not really like a very easy thing, just tell you in advance. And so I think the whole purpose of this lecture is because when we read a lot of paper talking about the FEA analysis in orthodontics, and like there are a lot of terminology and everything, and I hope this lecture can help you better understand when you read those papers, like stress analysis in orthodontics or FEA analysis in orthodontics. So like common thing we see for this one, when you see this in paper, like you probably would wondering why we do have this triangular thing in the structure. What purpose of this have this triangular thing? And also, let's say, why we can use spring system to replace the muscle in our stress analysis. And we talk about like what function of spring and what function of the muscle and why it is similar. And also things like here.
So the slides, feel free to interrupt. Everyone got that, the second one. Yeah, the muscle and the
spring system
analogy.
Yeah.
So as well, if the muscle is a spring, so they think the muscle is a spring.
So in mechanical engineering, it's all about math. So it's functioning the same way. In terms of math, it functions the same way. So probably all of you learn from like in high school, middle school physics, F equal to K times X. That is the spring system. You got to remember that one, right? So K is stiffness of the spring system. And for the muscle, if it's like in an elastic material and it can only carry the actual force, tension, compression, mathematically it's the same. It's still F equal to K times X. So that's why in FEA, we can use spring system to replace muscle. We can talk about a little bit more in detail later. So this is more like the introduction part. And another thing that I keep get question, like what is the von Mises stress? What is the different color of the von Mises stress? So we talk about that later. And also like how does FEA actually calculate displacement? Do they calculate displacement first or calculate stress first, or from stress to displacement or displacement to stress? How it actually works? I mean, we import the CAD model into the APS or ANSYS, and how does it like what it calculate behind the things? So, and also why here they put as equivalent stress, why von Mises stress is considered as a equivalent, what kind of equivalent is here? And also here, third principal stresses. I mean, what is the principal stresses? Why third principal? What is third principal stresses? So let's start from beginning. Of course, we need to start from the statics, force equilibrium. And this is, we simplify everything in 2D plane situation. Then this is probably something similar to your high school physics. So for a structure considered moving in the 2D plane structure, we should have force in the x direction equal to 0, force in the y direction equal to 0, and a moment about that z-axis. So let's say if you have a plane, x and y axis, so I have different force applied on this structure, but everything should be staying in equilibrium. So there should be no like acceleration in this direction, no acceleration in this direction, just no angular velocity in this direction. This direction. So basically, what we need to do is that force in the x direction should be equal to 0, force in the y direction equal to 0, and also this. So this is for 2D situation, simple situation. And of course, these are different boundary conditions. We don't need to know of them, but I just show you here as example. So let's say if you have a tooth and it's only moved in the 2D plane, it can be in this plane. This is, she gave it to me several months ago. She gave it to me several months ago. So let's say you can only move in the 2D plane. And you consider, if you do the free body diagram of this tooth itself, the force you apply, let's say you have attachment, you have wire or anything, the force applied on the tooth, and the PDL connected with the bottom part is considered as a reaction force. So in different boundary condition, it provides different reaction force. So PDL is basically, it fixes the whole bottom part. And in FDA, we can consider it similar as a clamp situation. So for this one, it means that for the reaction force, the bone combined with the PDL can provide the force in X direction, force in Y direction, and then moment to make your tooth in equilibrium. So this is for if we simulate things in 2D situation, and of course, in real life situation, it's a 3D. So basically mean that your tooth can have translation degree freedom in X, Y, Z, and they can also rotate about X axis and Y axis and Z axis. So 6 degree freedom, we have 6 equation. So force in X and force in Y, force in Z should be 0. Rotation or moment about X, about Y, about Z should be 0. So this is the main content in statics. So force equilibrium and how to calculate the reaction force and everything. And we know that when we consider, let's say, if you want to know the stress or if it causes the force applied, if causes the damage in your bone structure or in PDL or in any point you concern, we know that really the force is not the final answer, because let's use a simple situation. If we have a, let's say we can say this is a muscle or a spring or a bar, it's the same thing mathematically in the FEA. So you apply tension compression. I can apply a huge force, but at the same time, I can increase the cross section. It doesn't mean that it will fail. Larger force doesn't mean that it will fail earlier, because I can change the cross section and make the force intensity lower. And the same thing, if I apply a small force, it doesn't mean that it's safe, because if I keep minimizing the cross section, the stress or let's say the force intensity can actually increase and make it fail. So everything like students in mechanical engineering spend the whole semester talking about the force calculation, force equilibrium, moment equilibrium, but that is really just like a step in the middle. What we need to figure out is what actually is a stress. So that it becomes the content in the mechanics materials. So the simple situation, of course, we start from the tension compression. Tension compression, you consider this is same as the muscle I talked about, is same as spring system and same as 1D bar. It only carry actual force. So in this way, now you can see that stress is equal to the force divided by area. So it's more, you can consider it's a force intensity. Yeah, sorry.
Question.
Yeah.
Let's suppose we have a teeth.
Yeah.
We have a force coming, like pushing the teeth due to the movement, but we also have the teeth making the movement back to come back to the place. So the force, like pushing the teeth, has to be more than the force that is like trying to make the teeth be in the same place. So I want to know how you calculate that.
It's always in equilibrium. There's no like one force. Well, if you consider, let's say you separate your tooth from your PDL and bone, and if you check the tooth, do the free bar diagram with the tooth itself, it should be in equilibrium. Because if it's not, let's say, if one force, let's say if the force into the direction and the reaction force out of direction, they're not in equilibrium, it means that it has acceleration in that x-axis. So especially in your physics class, F equal to ma. Now your F, if let's say if all the forces are in the x direction and the sum of the force is not equal to 0, it means that there's a non-zero acceleration. So everything you may consider like one force is higher than the other, and it's not in equilibrium. But as long as your tooth stay there, it is in equilibrium. Yeah.
So the P here is pressure.
P here is a force. Yeah, P is a force. So basically, let's say this is a simple 1D bar situation. I apply tension, force upward, force downward, and then the force applied is P here, and the cross section, if I cut from here, the cross section is A, and for tension compression, the stress is uniform distributed, so the stress is simply F of A. Because since it's uniform distributed, no point is higher, like stress intensity higher than the other point. So this is a simple situation for calculating the tension compression situation. But of course, we have bending. So in your chalk talk yesterday, said I remember there was one faculty asked like the convex, concave, and one side should be in tension, one side should be in compression.
That's Dr. Gucci's question.
Yes. So
Yeah, can you wait 2 minutes?
yeah.
I'm gonna ask questions.
Okay, ask questions.
Okay, so I'm here.
So like the forces balance out, but the tooth still moves. And I assume that's probably because like the dynamic equilibrium that like allows it. To
Yes,
move.
actually, that's a good question. So yes, the acceleration and displacement is two different idea.
Yeah.
So mathematically, acceleration is a derivative of displacement, right?
Yeah.
And for what you just say is that all material we're talking about, they are deformable. Some maybe like tooth is very strong, the stiffness is very strong. But if you consider like the PDL or more softer thing, the stiffness is different. So when you have a force applied, force stays in equilibrium, but it will generate a deformation in the structure. So let's say I apply this force upward and a boundary condition at bottom. So the boundary condition we apply a force downward. These two forces, they're in equilibrium. It should be the same magnitude, different direction.
Yeah.
But it doesn't mean there's no deformation in the bar. It can elongate. It's same as spring. If let's say you have a spring system, you can try to pull it, and there's elongation, very visible deformation, right? And then you try to push it, it has contraction. So force equilibrium doesn't mean that displacement is zero.
Okay.
Deformation depends on how deformable your material is. If you have rigid body, in real life situation, we don't really have like real rigid body. Everything is deformable. It's like some material like has higher stiffness, some material has lower stiffness. So it's the deformation is more visible to see or not visible to see. Yes.
Okay.
But acceleration and the displacement, they're completely different things. So if the force is not in equilibrium, and then let's say I have larger force applied upward, and somehow my hand does not have providing the same magnitude of force downward, then it means that acceleration upward. So basically, this force minus this downward force equal to non-zero, and that non-zero value equal to F equal to MA.
Okay.
Yes.
Yeah, that is.
Yeah. So that is the clarification of the displacement and acceleration and force equilibrium. So, and also this is the
I have one more question.
Yeah.
So I guess this is more for like the orthodontist here. But when you have braces, does over time, like, is it the brace itself, like it's moving slowly, or is it moves first and then you have the brace to hold it into place? Like, I don't know if that makes sense or not.
So the tooth moves, the bracket is
Yeah.
connected to the tooth,
Yeah.
so that is one body. But the way we put force on the tooth is through the bracket,
Okay.
okay? So what is giving forces to the tooth / the bracket is the wire we place in it and the size of the wire.
So like over time, the tooth moves when you have.
Because we keep increasing the size of the wire, so it
Okay.
engages in that slot or the prescription of the bracket, which is rectangular. So we give it a tip like that. So once, if it's a round wire, it keeps sliding, but in the x-axis, it's correcting the rotation of the tooth. Then when we put a rectangular wire that fits into the slot like very well, it engages that rectangular portion and corrects the torque of the tooth. So there are 3 dimensions that the wire is trying to control and move the tooth in. And for the higher or the stiffer the wire you get to, the larger the wire you get to, the more 3-dimensional control on tooth movement you get.
Okay.
Okay, and so initially, yes, you get more movement in that, like not in rotational terms. But if you want like space closures, we have to add additional mechanics to it, like power chains or elastics to literally pull the teeth forward. And those are not just through wires and brackets, we put elastics that are between the teeth. So like chains that go around the teeth, or inter-arch elastics that are like rubber bands that we make patients wear between the teeth that literally pull all of them together.
Okay.
So it's a lot of things that
Yeah.
go in it.
Yeah.
Did that answer your question?
Yeah, that's it.
Okay.
okay. So now let's continue for the bending. So tension compression simply is one, and the bending is basically just leaving some random thing at the prop here. Let's say for this structure, if you apply something like this, it will bend. And this one, it will also generate normal stress. You can see sigma x means x is in the x direction. You consider if this is the x direction. So it's still normal stress in the action in this direction. But now the equation is not f of a. It's the moment over the y. Y is basically if the cross section, this is neutral surface, and it depends on distance. So if it's moving away from the neutral surface, which is, let's say, y goes downward, y goes upward, and the stress will increase. That's why in the question yesterday, they were asking why. So there's a when it's bended, of course. Now let's say if I provide a bending moment like this, then the bottom surface should be in tensile stress, and upper surface should be in compressive stress. That was a question yesterday about the bending situation. And of course, the maximum is always MC over I. I is moment inertia. And for different cross section, I use the two simplest situation here. If it's rectangle cross section, this is B and H is the width and height, and this R is the radius of circular cross section. So different cross section have different moment inertia, but of course we can go much more complicated cross section. If you consider, let's say you apply this is clamped reaction force and apply a force, let's say in this way, then it will generate a normal stress. And now this becomes the cross section. And what's the moment inertia of the cross section? We can simplify this simple rectangle cross section. But if you go more complicated, we can calculate the moment inertia. And the y is basically whatever you have the neutral axis, you consider this y equal to 0. And when now this is y negative and that is y positive. So basically, it's a linear change because it's my of I. I is constant for same cross section, and is constant at that cross section. So basically, on the cross section, it is linear change. And that's why if we bend in this way, we would consider the top surface has maximum compressive stress and bottom surface has maximum tensile stress. So this is for bending. And I is not the area, it's moment inertia. Moment inertia.
Inertia. So you know how an object when you break an object that goes forward and it has to come back, equal and opposite. Correct me if I'm wrong. Is that inertia?
No, it's moment inertia is the cross-section property. So let's say if you have a rectangular cross-section and if this dimension is B, this dimension is H, and the moment inertia of this rectangular cross-section is this one. And if you have let's say for this one, this can be a bar compression. But the same thing, if I clamp on this side and apply a force like this, it actually generates bending moment because it's bending this way. And now this cross-section is circular cross-section. And how the stress change on this cross-section? Moment inertia is this one.
So change in stress distribution is what the moment of inertia
change of
You can consider is a bending rigidity. So if you have a higher moment inertia, it means that it can better resist the bending moment. And it generate lower stress because it's here. And similarly, in the F of A, if you have a higher cross-section, it can have larger rigidity to resist the tension compression.
So
Right.
the bigger the I, the
Yes.
and then you X, Y, what is C?
This is a more complex situation. So let's say this is considered if it's bending about one axis, but if you have bending about two axes, you have combined the bending moment. Yeah, but then in that situation, we have different. So basically, this one is different. Yeah. Now the next one is torsion. So torsion is also very common one. So basically, let's say again, I use this one example. I clamp on this side and apply a torque in this way. So it will generate a torsion. And now the stress generated torsion is not sigma, it's not normal stress, it's a shear stress. So it's just considering what's this one from that? And let's say if I put torsion is something like this. So now the stress generated in the structure is more like a shear stress. Tension compression is normal stress, but torsion is shear stress. So for different cross section, we have different polar moment inertia. The J here now becomes the polar moment inertia, and similar situation, of course, we have the circular cross section. This is the one we use to calculate the polynomial inertia for circular cross section, and this is considered as the distance from the center of the circle. Let's say if I have a point here, I want to know the shear stress generated by this same torque, then this distance becomes the rho. But if I consider the outer surface, now the radius of the circle becomes the rho. So again, when you see this equation, you can see that, let's say, torque is constant on the cross section, polynomial inertia, of course, is constant on the cross section. Then the shear stress on that cross section really depends on the distance. So basically, it means that it's zero at center, linearly increase to the outer surface. Outer surface has the largest rho here, so it has largest shear stress. And so now it makes sense when you have see a lot of structure in real life. Why they make the thin wall? Because only the outer surface it carries the maximum stress. And if you want to have a structure that survives that torque and not fail while maintaining minimum weight, which is very important. I don't know about orthodontics, but very, very important for aerospace because everything you want to fly, you want to have minimum weight. So that's why in a lot of real life application, when the major load is torsion, we normally put a thin wall. Material in the middle actually does not matter that much because the stress is just so low.
So you put thin wall on the outside small force.
Has maximum stress, maximum shear stress. For a material, it will fail or not, it's all because of stress. Yes. So now this is the for the torsion. I'm gonna yeah.
Variables you're using for the torque.
This is torque. T is torque.
Oh, okay. So I was like, okay.
Yeah, T is torque.
The same as the recent side.
So you want a thin wall so that you can resist the torsion?
The thin wall is more like an optimization of a structure. So because from this equation, you can see that the center of the circle, if it's solid, then this is the stress is zero. So put material there, not put material, it doesn't matter because it does not carry any stress. And now if you move away from the center of the circle, let's move in this direction, and the stress gradually increase, and the maximum is on the outer surface. So let's say if we want to design a structure that can survive a certain torque, but I want it to maintain the minimum weight. How to maintain the minimum weight? I remove the center area because the center area does not function much. So that's why you see a lot of tube kind of structure if the majority of the load is torque. And I think it also has application in the orthodontic because some, let's say, I don't know too much, let's say if it's already in this way, but it's supposed to be in this way. So you need to use the attachment wire and to apply a torque. And in this way, then it is the torque on this cross section. Makes sense or not? So that is a shear stress generated by torque. And yeah.
I heard a saying that's torque, like the torsion. Like
Yes.
Multiple.
No, it's a different thing. So let's say tension compression. I apply force upward, reaction force downward. This is tension compression. Yeah. This is tension or it's compression, right? If I let's say bend in this way, I try to bend in this way. This is the bending moment. Torque is, let's say I still clamp here, but I apply a torque in this direction about the axial direction. It's a rotation moment about the axial direction. Then it becomes a torque. So it's a completely different thing. Tension, compression, bending, and torque. Yeah.
And so torque is unique for, like, torque is what we provide the object. It's
torque is one type of force in general term. Yeah.
And then the torsion is a material property.
Shear stress is the stress generated by torque. Torsion is just a failure mode.
Okay.
Yeah. So so this is for torsion, and we have the other cross section. I think I'm gonna skip those. The last one is the transverse shears. Transverse shear is also let's still consider we clamp on this side and apply this force. So of course it will generate bending moment because whatever force you apply here times the distance. If I want to know the bending moment here, then distance this is the moment arm. So force times the moment arm, put the moment. And of course, as we know that since it's a 4 times distance, we know the maximum moment should be here. So this dimension times force equal to maximum bending moment, and maximum stress should be on this cross section. At top and the bottom, of course, maximum compressive, maximum tensile. The transverse shear is basically when you apply force in this way, it also generates transverse shear at the same time. So I still use this one as example. So tension compression, and torsion and bending moment bending this way. Transverse shear basically means this is shear. Let's say I clamp on this side, I fix this side as a reaction and apply a force here. Then this is transverse shear. And for calculating the transverse shear stress generated by transverse shear force, this is the equation, and it is the shear force, first moment area, this thickness dimension of the cross section, moment inertia. So the different thing is that, as you can see that for the torsion, it's linear change for the stress level. For bending moment, normal stress caused by bending is also linear change. And for tensile, it's uniform distributed. For this one, it is quadratic change. It's because of the equation itself. We can talk about this in detail later, but I don't think we have time, like a wide quadratic change for rectangular cross section. But we need to know that for the shear stress distribution on the cross section, it normally starts from 0, end at 0, and maximum at neutral surface. So this upward, if I apply force upward, this is the shear stress direction in terms of magnitude change in this way if it's a rectangular cross section. And if it's circular cross section, we put in here the moment inertia and also the first moment area, and you can derive, and this is the maximum stress. They're both at the neutral surface. So these are the different components. And of course, sometimes it's not just simply tension compression or only torque applied or only moment applied or only transverse shear applied. It may happen in a situation that we have all of them. So what we need to know is that stress components at a point. So back to the introduction part. Let's say you apply force through the teeth, and let's say at this point, it may have tension compression, it may have bending, it may have torsion, it may have transverse shear, all those combined together. And we want to know what is the actual stress there. So what we can do is that for that specific point, when you combine all those stress components, we can have a global coordinate system. And we have, based on this global coordinate system, we have this is X plane, because if you have normal vector on this plane, it's in the X direction. And the same thing, this is the Y plane, and this is Z plane. And these are in 3D space, they're independent 3 axes. And on each surface, we have normal stress. So we put it as sigma xx, sigma yy, sigma z. Whenever you see sigma, it's normal stress. Whenever you see tau, it is a shear stress. So on this X plane, it has shear stress in Y direction, X plane, Z direction, and similarly in all the Y plane and Z plane. So now for a state stress at a point, if you want to completely define the state stress at a specific point, we actually need these 9 components to form the matrix. And now it comes to when we see the third principal stress, what does really third principal stress actually means? From here to here is so this is the state of stress based on coordinates we define. We can calculate normal stress generated by tension compression, by bending, or in the Y direction or in Z direction, or shear stress caused by torsion, caused by transverse shear. We calculate all of them, and based on coordinate system, we put in the matrix. And now the principal stress, the basic idea is that, let's say, this is global X, Y, Z coordinate. And when we want to know it fair or not, there's a specific plane not really aligned with some global coordinates. Maybe you rotate the cube, and then in some certain orientation, all the shear stress disappear, and only the normal stress exists. So in that situation, it becomes the principal stress. And mathematically, how do we get the stress component in global constant and find the maximum principal stress and all shear stress disappear? It's an eigenvalue problem. So eigenvalue problem, you probably learned from somewhere before you come to Earth. So you have minus lambda, minus lambda, minus lambda, and make it determinant equal to 0, and all the 3 lambda become the 3 eigenvalues of a 3 by 3 matrix. Make sense? So of course, if you have a matrix, you should.
I have no clue.
What is lambda?
But are you talking about? Right.
Anybody know what is eigenvalue? No? Okay, then let's give it. So I think it's in the calculus or something, linear algebra. You learned before. Okay, great. So it's in the linear algebra. So basically, for this 3x3 matrix, you have the eigenvalue. You on the old diagonal term, you minus lambda and make this 3x3 matrix equal to determinant equal to 0. And you can Google check how to calculate determinant matrix. It's a very long story. And then when you set this one equal to 0, you have for 3x3 matrix, you have 3 eigenvalues, and those 3 eigenvalues becomes sigma 1, sigma 2, sigma 3, 3 principal stresses. And the physical meaning is that in the global x, y, z coordinate, you have the stress component on the x plane, y plane, and z plane. And now it probably will not fail on this plane because this is just like before you do the analysis, just use global coordinates. But I want to know when it's gonna fail. So I'm gonna rotate this cube. And on the plane that, let's say if it failed because of principal stress, I want to find the orientation that the plane has the maximum stress. So that is situation that I rotate to a certain orientation, all the shear stress disappear and only normal stress stays. That is the physical meaning of the principal stresses. So now it comes to why do we need this one? If any of you learned material science, you know that. So for the material, how the material will break. If the material is a brittle material, let's say, as an engineer, I can only use example. Let's say glasses, ceramic, those material, they are brittle material. They are breaking because they fail because the breaking because between the atomic bond, the atom bond between them. And for the metal we normally use, let's say for aircraft we use aluminum, those structure it fail because of the sliding of the atoms in the microstructure way. So that one means that for the ductile material or metal, mostly we use, it fail because of shear stress, because of sliding of the atom layers. But for the brittle material like glass or ceramic, it because the breaking of the bond between atoms. So that is fail because of normal stress. So if we could find the orientation that normal stress reached maximum, it means that that is a plane, it will fail. Make sense or not? So now it comes to the failure theory. It depends on what material you use. If it is a brittle material, it failed because of principal stress, so we have maximum principal stress theory. So again, back to the screenshot from the paper. What is third principal stresses? Actually, that paper is a mistake. They should not compare the third principal stresses. The convention is that from the engineering point of view, the convention is always the maximum should be the sigma 1, and then the second one sigma 2, and the minimum is sigma 3. So the maximum principal stress is always sigma 1. And so now we know that if it has a brittle material and it failed because breaking the bond between the atoms, so it failed because of normal stress. And when we find the sigma 1, it means that it will fail, right? And for some material, let's say it failed because of sliding between the atom layers, so it failed because shear stress. So in this way, we need to find the maximum shear stress. Actually, I can put it here. The shear stress equal to half of the sigma minus sigma 3. Again, there's a big story behind this one, but now you can just accept. When we have the principal stress, sigma 1, sigma 2, sigma 3, how to calculate shear stress is basically tau, the maximum shear stress in the structure equal to sigma 1 minus sigma 3 half. And now we use this to compare with the shear stress in the materials. Let's say if you use aluminum, you know what is for specific type of aluminum, you know what is the yield strength, what the allowable shear stress of the material. So you can compare if your structure will fail or not. And again, back to the screenshot of von Mises stress theory. Now this is von Mises stress. As I said, it's a 4-year class, so I cannot really explain like in a very short time. So this is von Mises stress. So basically, you calculate principal stresses first, and von Mises stress theory is also called distortion energy theory. So basically, it's not comparing the maximum principal stress or maximum normal stress or maximum shear stress. It's comparing a distortion energy. So basically, so for each material, we cannot really do for different application, but for each material we have, what we have is that in the lab, we can do tensor compressor tests. So you fail, it has a distortion energy before it fail. So we know that distortion energy, and in your own application, let's say you have a your tooth and you apply different force, and then you know what is distortion energy in your own structure, and you compare distortion energy in your own structure with the tensor compressor test of the material, and know when it will fail. And then for comparing the distortion energy theory, distortion energy, we consider this is the energy, the theory based on the energy, but when we calculate, it actually becomes a stress, and we consider the von Mises stress is not a real stress. It's a simplified, it's an equivalent stress when we have different stress components and we want to find a single equivalent value and compare with yield strength of the material. That's why when you see the screenshot I showed at the very beginning, you sometimes say that it's von Mises stress, sometimes you say it's a equivalent stress. It basically means that when you have a complicated structure, let's say you apply force, it can be the force inside or upward or apply a torque, all those forces applied at the same time. And for the stress generated at a specific critical point, it does not necessarily only the tensor compressive, it does not only the bending or only the torsion, it's combined everything. And with so many stress, I mean, which one do you want to compare with allowable stress of material? There should be one single equivalent value. And the single equivalent value here is the von Mises stress. And this is based on the distortion energy stored in your own structure and distortion energy we do in the lab test for that material. And if the distortion energy in your own structure exceeding the 1D tension compression test, before it fail in the lab, it fail.
So that value, the sigma y fail, is those.
This is a material property.
Yeah, so that's
Yes.
got from a lab value.
Yes,
And
yes,
so if we compare that with
yes,
our structures to
Yes.
see the strength, compare it to the lab value.
yes. So basically everything on this side, they are whatever material we have, we only do tension compression tests in the lab. And we test what is the yield strength, everything else. And everything on this side is the actual stress in your own structure. And you compare. If, let's say, if it's brittle material, if the maximum principal stress exceeding our allowable stress of the material, fail. If it's ductile material, and then if the maximum shear stress in your structure is greater than allowable shear stress of the material, fail. And here is the distortion energy stored in your own structure is greater than the tension compression test distortion energy, it fail. So we cannot really say like which theory is correct, which theory is wrong. I mean, we use different model to do a prediction. And of course, we know that for brittle material, we have one to choose, and for ductile material, either this one, this should be fine. It's just different one propose different theory. So that's why when you see like it always show von Mises stress, sometimes it shows shear stress. Hope this can help you understand that part. And do you want to continue? Okay. Let's skip some part. So I thought to use this example to simplify, like you have a tooth and you have the jawbone and you have calculate the maximum stress. Actually, it's similar as what we did in mechanical engineering. You have an L shape and you apply force. It's similar as you have force applied on the teeth, and then you calculate the maximum stress here. It's kind of similar situation. So it's more like you calculate all the normal stress caused by tension compression, normal stress caused by bending, and shear stress caused by torsion, shear stress caused by transverse shear, and then you put into a static stress matrix, and you calculate eigenvalue, you get a principal stresses, and based on different theory, use different theory to know. That's why in the paper, they normally show like the final answer von Mises stress, why. Here is why, yeah. So let's skip this part. And also, yeah.
I remember like a long time ago, someone did like a paper on like about the axes, like the points of which like the tooth moves, like in like certain like directions. It was like the tooth has like a tipping point and it's like further down, like across like the root. I forgot who did that. So my question is, if we have like the bracket on the tooth, like how can we like apply pressure for it to move in like just one direction? Like just like for example, I guess like what I don't know, like the Z.
Just in the x-axis.
Yeah.
y-axis. Yeah, so it's very difficult.
Yeah.
Which is why so the bracket is made three-dimensional changes to the tooth. So whenever you put a wire in it, if it doesn't fit all the way, it's not causing the x direction forces.
Yeah.
Not z direction forces.
And
So
if
it's
it's on,
very
like-
hard to control that.
If it's like the bracket's on like one spot and like you're
So
applying
your
pressure, what about like
Center of
torque?
rotation.
Yeah.
So force is gonna reach to the center of rotation of the object and it's gonna cause motion. So the
Okay.
distance that we bond our brackets to is very important because the greater the distance, greater the moment, more the rotation. So
Yeah.
it is very well taught, and how we place it is like full science.
Okay.
Yeah.
Yeah. That's what I'm.
We just don't place brackets anywhere.
Yeah.
We place it at the point so that we can control where.
Does
the
it like
point
differ
is.
from person to person? Like,
Yeah, yeah.
And
If
so
you
then how do
have
you,
a
like,
few-
No, for like person to person.
through x-rays, through clinical findings, all of that.
Through artistry.
Yeah, actually, I can talk a bit more about using this one. Let's say even we only apply a single force here, what do you see? Just a one force. But actually, if you consider, well, for this force, of course, if you define this x coordinate, this y coordinate, or let's say this is the y coordinate, doesn't matter. Then this x component will generate tension compression in this section. Make sense or not? This x component will generate tension compression, and this x component also generate bending because there's a moment arm here. So this force times this moment arm become the bending moment about y-axis. And so it should also has normal stress at this location. Of course, we know this is the critical location, so we only focus on this point. And same thing for this, similarly for the y component, it will generate a torque. Because now, if you just imagine you have force in this way, and this is the distance, and now this force times this becomes a torque, and it actually can rotate about this x-axis. So this becomes torque, and of course, you can calculate TR over J, calculate the shear stress here. And this one also becomes the transverse shear, because if you just imagine, let's move it like equivalent here, it actually is a transverse shear. So it will generate a shear stress caused by transverse shear. So in the end, it's not really one component. So it is multiple stress component caused by different failure mode. And back here, we calculate all those stress components, we calculate principal stress, we use different failure theory to decide if everything's okay. So this is the basic procedure, and this is everything all in mechanics materials. And of course, I think in the meeting last week we talked about like the muscle, like open position, closed position. So that's a different topic. So it's basically a fatigue problem. So you open, I would imagine that it has generate larger stress in that position, because let's say you have a spring system and elongate it more, it has larger force, it will generate larger stress. And now in the closed position, the muscle is like the elongation is much smaller, the force is much lower. So it's more like a tensile back to zero, tensile back to zero, tensile back to zero. And even the maximum tensile stress at that location is really not that really damage any structure, cause any pain on your bone. But if you keep that open, close, and just imagine like how many times do you open, close every day, you can consider what's the accumulated damage, and that is considered as a fatigue problem. So, but for the specific fatigue, I'm gonna all this content, and also stress concentration. If there's a sudden change of structure shape, is a stress concentration. But let's move to the FEA directly. So that is everything like I talked about bending, torsion, tension, compression, transverse shear, and everything. That is like one simple structure you calculate. But in real life situation, it's more something like this, or in this structure. So that's why we need the FEA, because you cannot really calculate everything based on a simple bin, a simple bar, or an L shape. It's not really just an L-shaped structure. You have so complicated structure. So what do we do? That FEA is the finite element. It means that it discretizes your real structure into small elements. And now each element, let's say for this one, if you take this section, each one become a single bar. And each bar we consider one element, and for a completed real life structure, we assemble them and use software to solve them. It cannot be done by hand calculation. So, and also this is a plane stress situation. When we can simplify as a plane stress, when the stress in the third axis is much lower than the other two axes, we consider plane stress basically is a stress in 2D plane. We can use the rectangular element. We can use the triangular element, and this is what we had in the previous work, tetrahedral element. So this is basically solid model. This is more like we talked about it before, like STL file is surface model and everything is in surface model. So that is we can consider it's a plane stress. There's no stress in the third direction. But for our simulation, we always need to use a 3D simulation. So now it becomes the tetrahedral element. And again, now each tetrahedral element, you have a stiff matrix, and you calculate, consider it's like each element is one component we learn in mechanics materials. And now we assemble all of them into a whole system and do the calculation. That's why you come to keep crashing. I can explain what is Abacus really doing behind why is keep crashing. So again, start from the simplest element. We have the three. Let's say from the mechanics materials. And now this is a KQ equal to F. U is the displacement you just mentioned. So when you have force applied, you have stiffness, you can use the calculate displacement. So this is the displacement part. And for the one bar, now let's say if we move to the 2D space, this is a stiffness matrix for one bar element in 2D space. And this phi angle is angle with x-axis. And when this bar can move in the 3D space, each node has a 3-degree freedom. We have one element have two nodes, so it becomes 6-degree freedom. So the matrix becomes 6 by 6, still one bar element in 3 space. Now let's move to the bin element. Let's say if we have a single bin element, and this is stiffness matrix. It depends on the Young's modulus, depend on material, depend on the moment inertia, depend on the L of the length and of the length of the beam. So this is a stiffness matrix for one beam element. Now this is for plane stress situation. Let's say if you have a square element, let's consider this is a plane stress situation, and you have a square element, and we have 4 nodes. Each node can move in X and Y. So 4 nodes, we total have 8-degree freedom. So the stiffness matrix becomes 8 by 8. Now let's move to the tetrahedral element. So you can just imagine how complicated it is. This is for one single element. 8 by 8 is for 4-node rectangular element in 2D space. For this one, it has 4 nodes. Each node can move in X, Y, Z. So for the stiffness matrix for this single element is 12 by 12. And now what do we need to do is that for each element, we have the 12 by 12 K matrix. We have displacement for 4 nodes. Each node can have 3 degree freedom. So this is the vector of the 12 components. And a force, of course, corresponding 12 components. And now you have so many tetrahedral elements.
And how do we decide the distance?
So how the Abacus work is that you import a model that will generate the stiffness matrix. You apply force and boundary condition that will generate this vector. And Abacus will calculate inverse of this matrix times the force vector, and it becomes displacement. What do we need to calculate? So that explains why if we cannot a smooth model, it will keep crashing. It will never work. So the only way we can make it work is that we make the whole structure very smooth, and we use larger tetrahedral element. So the workload for the Abacus is much lower. Yeah. So I just use a very simple example to show you here, like how does Abacus do the calculation. But this is a very simple 2 triangular element in 2D space, and only 2 force applied. 1 force is in the X direction, 1 force in direction, and this is 2 triangular elements assembled together. Just show you a very basic procedure how the Abacus do the calculation. But of course, for tetrahedral element, it's much, much more complicated. Just show you the basic procedure here. So first, based on the coordinate of each node of the triangular element, we have 2 elements here. We calculate the B matrix C matrix is the matrix connecting, converting the strain to the stress. B matrix is converting the displacement to strain. So now we have the thickness of the triangular element times the area of the triangular element, B transpose times C times B. We get the stiffness matrix of the one triangular element. And we repeat the same thing for the second element, and we get the K2 means the stiffness matrix for the second triangular element. Now, back to the picture. That is K for element 1, K for element 2. And of course, these two elements, they are connected on this edge. So we need to do assembly based on the connectivity. And this is after assembly. Put two elements, and we have two nodes connected. So we have the corresponding components we need to add together. So this is the 8x8 matrix for this structure. We have 4 nodes. For the whole structure, we have 4 nodes. Each node has 2 degree freedom. So it becomes 8x8. And we apply boundary condition, and we solve for the displacement. And of course, the other that's not written here, like U1, U2, U4, and V4, because they are considered as clamped here. So this 0 here and 0 here. And so we solve for all the displacement. And for calculating stress, what abacus need to do, or FA, what we need to do is that this is all the displacement times the B matrix, we get a strain. And from the strain, we times C matrix, C matrix times the strain equal to stress. So this is stress in the first element. We repeat the same thing. This is node degree freedom. B matrix for second element, strain in the second element. Strain in second element, C matrix of the second element, stress in second element. This is the procedure-wise how to calculate the stress in this structure. Just 2 triangular elements, 2 force applied, 2D situation. So now you can imagine you are doing this, importing this kind of thing in abacus. So the key point is that we really need to smooth the structure, make smaller number of elements. Otherwise, it will not work. Yeah.
For context, my model had 1 million triangles.
Okay, huge element.
Elements.
That was right.
It sends it to the cloud, so no matter what.
Like you ain't got like a supercomputer just with.
So here the thing is not just a computer thing. So let's say for abacus, we have the student edition, free edition. We use for teacher class. It can only use up to 1,000 nodes. Anything higher than 1,000 nodes, it does not allow you to import. We are using the research license, but still it's not like, it's hard to solve something like this. Yeah, it's just too much.
At a point, it plateaus, right? The accuracy plateaus. Like, no matter if you did 1,000 triangles versus 10,000 triangles, there might not be a difference. So we have to do
It converge.
Yeah, they converge. Yeah.
Yeah.
I'm not sure how much everybody gets. I think it's too advanced for me. But let's take a photo together.
4 years, 4 years class. Here.
Very nice, Dr. Dong.
Thank you. Which picture should I use?
I like scroll down. The multicolor one.
Better than like.
This one?
Like this one's cool.
Which one?
The one above.
Nobody's here, so I
I'll
take
it.
No, yeah,
you
can take it first.
Let's use let's use
Good.
which one I like most.
Yeah.
Let's use this one.
Yeah.
Okay.
Let's use this one. This is nice. Right here, everybody.
Yeah, that was good.
你在中间。
Maybe we need 2 lines.
Yeah, we need 2 lines.
Yeah. One.
I was ready.
You were so ready. We're stuck in holiday.
1, 2, 3. I'm trying to understand.
Balance.
Yeah.
How many questions? Ask any questions. He's the first time, right?
I never seen it that quiet.
I was waiting, I was like, alright. Have for paper, have something for storage. You want to show? Yeah, I bet.
Thank you.
I like that.
This is good presentation.
That was good.
Yeah, I get it.
I know, that actually helped a lot.
Last part, yeah.
Because when you say tetrahedral element, I was like, tetra means 4. And then I'm like looking at this picture, I was like, these are, but now I see. No, I get it. Yeah. Yes, you are. So at least in this GeoMagic, it's
Wow, I'm so proud of you for making this work, Matthew.
Thank you.
So, when you were saying like, I don't know, like I find that really cool. How you guys have to work on it before too. Work on it more.